Well, hello, my Integrated Science 2 class. I'm going to try to do a couple of these problems on the worksheet called Mechanical Advantage of Levers, and hopefully I'll do enough that you'll be able to finish this. We may split this into two screencasts, so we'll just see kind of where we go here. We went over a little bit of this in class the last time we met about the mechanical advantage of a lever. And we're going to primarily deal with the second equation here, where the mechanical advantage is equal to the length of the input arm divided by the length of the output arm. We're going to call that D in and D out. Remember, the length of the input arm is measured from the fulcrum to where you are applying the effort, sort of where your hand would be. And the length of the output arm, what we're calling D out, is always measured from the fulcrum to wherever the load is, or whatever it is you're trying to move or lift. So we use this one as an example, where a construction worker uses a board and log to lift a heavy rock. The input arm is measured from the fulcrum to where the input is. So here's the fulcrum. So it's measured from there to here. So that length would be 3 meters. And then the output arm is 0.75. So that's measured from, again, the fulcrum to here where the rock would be. So that is 0.75 meters. And the mechanical advantage is simply what we call the distance in, and this is your distance out. So we have D in over D out, 3 meters over 0.75 meters equals 4. So it's sort of multiplying the effort of the construction worker by 4. He can lift 4 times as much compared to what he's pushing down on that lever. On a second class lever, in this case this is a third class lever, sometimes they're used to multiply distances. So a broom would be a good example. Or again, any kind of stick used in sports like a baseball bat or a lacrosse stick, where one hand serves as the fulcrum. So the top here of the broom, this is sort of your pivot point. So this would be like a fulcrum. And then we measure the input force from the fulcrum to where your hand is applying the effort. So this distance of 0.3 meters would be your D in. And then some of this looks like it's overlapping. We're actually measuring from the same spot, the fulcrum, beyond that all the way to where the output force is. So your 1.2 meters would be your D out. And when we take distance in divided by distance out, 0.3 meters divided by 1.2 meters, we get 0.25. So you do have a mechanical advantage here that is less than 1. That is okay. Sometimes that's desirable. It means that the machine multiplies the distance. Of course, that's why you would use a broom. That's why you can sling a ball as fast as you can and as hard as you can with a lacrosse stick. The reason you can hit a tennis ball or hit a baseball or hit a golf ball as far as you can. So let's go ahead and try this very first problem. This says a lever is used to lift a heavy box. You have an input arm of 4 meters and an output arm of 0.8 meters. This could be either a first or a second class lever. So let's draw it as a first class lever. So what I would expect you to do this is put a fulcrum in, draw a lever, and you can try your best to do it to scale. Here would be what we're trying to lift. So here's our load. And we're applying our effort here. Remember, that's called force in. And we measure from the fulcrum to where we're applying the force. That's our distance in. And we measure from the fulcrum to the load. And that's our distance out. In this case, the input arm or distance in is 4 meters. The distance out is 0.8 meters. So our mechanical advantage, in this case it's the ideal mechanical advantage, is equal to 4 meters over 0.8 meters. The meters cancel. We're left with an answer of 5.